the behavior of the nature around us, which is physics, chemistry, and biology, ultimately is rooted in the laws of quantum mechanics. And solving quantum mechanical equations on a regular computer is extremely hard. But actually, a very nice example which tells you how, by starting with a superposition state, you can operate on all of them, and how, as the algorithm progresses, the correct answer's probability increases while the wrong answer's probability decreases. So it really contains both these nice aspects in that. And the advantage is that instead of n by 2 steps, you can get the answer in about square root of n steps. So in fact, you get some completely crazy answer, is that if you have a 1,000-digit number, a regular computer would take something like 10 to the 24 years. I mean, this is an unimaginably large number, whereas a quantum computer will only take 20 seconds. So it's basically an impossible problem becomes possible in very quick time. Quantum computing is actually a very complicated topic, and even I wouldn't call myself an expert on all the aspects of quantum computing, and I hope I will give you a flavor of what it entails to be in this field, and what are the kind of specific things I'm focusing on, and what others are doing, and why this is such an exciting upcoming technology, which world over there's a huge amount of excitement, and including in India, where the research in this area is actually picking up pace. Okay, so before we actually jump into quantum computing, even though now you've had some introduction to what quantum mechanics is, I want to come back to give you a brief sort of reminder. And again, many of you might already be familiar with these ideas of how does actually basic computing work. How does it work in the computers we use today, which is now we call it classical computing. Okay, so let me start. So this 20th century has often been called the information age, where computing technology has really revolutionized how we do all kinds of things, especially towards the later half of the 20th century, which is of course now over, and we're well into the 21st. But all of this was possible because of the possibility of manipulating information electronically, using this idea of representing information in the form of a bit. So most of you have heard these terms now. A lot of you use computers for programming and everything. Your phone memory is represented in gigabytes these days. I remember when I first bought my first PC, it had, I think, 20 megabytes of memory or something. That was a while back. So the thing I want to point out here is that we call these basic units or elements of storage as a bit, which is often represented as a 0 or 1, which means these can take two different possible values. But the examples I've shown around this in this figure are talking about storing the same information but using different physical systems. Okay? And this is something important to keep in mind, that you always need some physical system to store the information. It is stored differently in a compact disk or a DVD disk versus a magnetic hard drive, or inside your computer, or inside a flash drive. A different piece of physics goes in how the states corresponding to 0 and 1 are stored. So for example, in a CD or a DVD, they correspond to microscopic defects on the surface of the disk. And there are two kinds, one representing 0 and one representing 1. And by using a laser light, you can actually figure out which is what. And by making them very, very small, you can pack a lot of that information in there. But exactly the same information on a magnetic disk drive is stored, in the magnetization of the domains which are present in these disks. So, it's very simply put, it's like the North Pole and the South Pole pointing in different directions can be one way of thinking about it. That's oversimplifying it. And then similarly, it's slightly different in a flash drive or inside your computer. But you need a physical system to first store this information. So any system which can take two different values, that's why often you hear that, a bit is like a switch, it's like on and off. So you have two physical states, okay? Now, building upon that, when you talk about doing computation or operations, we are now talking about building up from very basic elementary operations like adding numbers, right? So we all know how to do this. It's very simple. We can even add larger numbers, but then you say that, okay, how do we do the same rules in binary? And it's really just counting, right? You're just talking about increasing this element one by one, and as you run out of digits, you then increase the next digit, and then so on and so forth, and that allows you a way to advance numbers. And this is, of course, the familiar decimal system, which has 10 different digits going from 0 to 9. But the binary system, which is a special system for numbers, uses only 2. And I'm sure many of you know that there are many different number systems you can use with 2 digits, 3 digits, 4 digits, and so on and so forth. But the two most commonly used ones are the decimal, which we use for all our regular computations. But computers and electronic instruments prefer to use this binary system. And this is because it's easy to make something which has only 2 distinct states as opposed to having 10 different states. There's fundamentally no reason why you couldn't do it with a different number system. It just turns out that binary is sufficient and it's very easily implementable. And that's why everybody uses binary in this kind of, when you are talking about implementing computations in a circuit, okay? So again, we know how to map decimal to binary. So you start with 0, of course, then it's the same. You go up to 1, you have 1 in binary, but now you have run out of numbers. So the next thing to do is the 1 comes back to 0, and then you put another 1 here. And so this 1, 0 represents the decimal number 2. Similarly, now you add 1 more, it becomes 1, 1, that's 3. Now you have again run out of digits in binary, so this becomes 0, that one becomes 0, and then this becomes 1, which represents the number 4. I could choose to represent this using 3 binary digits and sort of make them uniform. So then this would be a representation of these decimal numbers in binary form, right? And the way you increment is exactly the same logic we applied for decimal numbers as well. You keep incrementing it till you run out of digits, and then you have to move over to the next decimal or the next digit place in this case, okay? So how does the operations work? I mean, we already discussed this. You can write the same addition of numbers in binary, and you do the same thing. So 0 plus 1 is 1. 1 plus 1, now you don't have, you know, it's 1, 0. So you put a 0 here, carry forward 1, and then you get 1, 0, 1. Right? Now, the point is that we want to be able to do these operations on a machine. So we try to look for what is the logic here. Right? If you now look under the basic elementary operations happening, what does it mean to add numbers in binary? It turns out to be extremely simple map, right? If you have 2 zeros, then they would add to a 0. If you have a 0 and 1, it adds to a 1. If you had 1 and a 0, it also adds to a 1. But if you have 1 and 1, then it basically gives you a 0, but then you remember you have to carry over 1. So we need some mechanism to mimic this operation using some electronic device. And that's basically what the basic elementary circuits do. And these are built using elementary components called gates. So for example, there is something called an XOR gate, which has a mapping like this, which is often called a truth table as well. It basically tells you what is the output given all the different possible inputs. So since there are only 2 binary digits here, 2 bits, there are 4 possible inputs, and then for each of those 4 possibilities there is a particular output which comes here. So if you look carefully, this XOR gate has the same property which we had just discussed in the previous slide. The 4 possibilities are 0, 1, 1, and 0, and they correspond to the 4 different possibility of addition. Remember, these are the only 4 possibilities for adding 2 binary numbers. There is nothing else, 2 single-digit binary numbers. Right? So that is called the XOR gate. And then there is something called an AND gate, where you have the output as 0, 0, 0, and 1. Okay. Now, typically when we explain this, the logic we say is that, okay, an XOR gate has the logic that if the numbers are the same, then the output is 0. But if the numbers are different, so here 0 and 1 are different, then the output is 1. That's the logic behind the XOR gate. But that logic is the same as adding 2 binary numbers. And for the AND gate, we say that if only if both are, the inputs are 1, the output is 1, otherwise it is always 0. Now, what does this logic represent? It's actually the logic for the carry forward. Because if you remember, in all of these operations, there was no carry for the first 3 operations, and the last one you had to carry 1. So you can see that with these 2 different gates, you can implement a very basic addition of binary numbers. So you can use the XOR gate to give you the sum, and you can use the AND gate, which gives you the carry. And essentially, all of electronics is just a combination of many such elementary operations to make it more and more sophisticated. And then you, of course, have lots of instructions which give you bigger, more complicated calculations. So here is another type of gate, which is called the OR gate. And it differs from the AND in the logic that even if one of the inputs is 1, the output is 1. Whereas if only both are 0, the output is 0. So there are many different kinds of such logic gates, but there's one special kind, which is called the NAND gate. It's actually the same AND gate we had, but then inverted. So instead of having 0, 0, 0, and 1 here, it's the opposite of that. So all the zeros become 1 and all the ones become 0. And that's actually what this is NAND stands for. N here stands for a NOT, which is basically an inversion. So 0 becomes 1 and 1 becomes 0. Okay, and it turns out that you can make all the other logic gates using just this particular NAND gate. So that really is very useful from the point of view of building electronic circuits, because you just have to manufacture one type of a device, and then you have lots and lots of them, and to give you more and more complicated logic. So for example, an AND gate can be built using 2 NAND gates in this way. Similarly, an OR gate can be built using 3 NAND gates in this particular way. I'll not go into the details of how it's worked out. You can actually look this up fairly easily and see. So this is essentially the idea, is that you can now have these very simple fundamental building blocks to do more and more complicated calculations. Okay? And this is sort of the essence of how classical computing works. You have these 2 states, and then you can do some operations on them to create logic. And then with that, combining that logic, you can carry out lots of different operations. Okay? And to sort of elaborate on this a little further, you can think about how a NAND gate could be implemented with a simple circuit like this. So here you just have a battery and a resistor which is driving, some lamp, and you can see that only if both these switches are open, there will be a current flowing through the circuit and the lamp will be on. If both of these are closed, then this thing will short circuit the lamp and it will not run. And even if one of them is open, it's still okay. So this reproduces the NAND gate logic. So this is another way of thinking about it. In a real system, in computers and other electronics, it's actually done using something called transistors. Maybe the 11th and the 12th class students might have seen a symbol of a transistor, but this is just really to show you. And these transistors can be made extremely small. Here's a picture of what a transistor looks like in one of your computer chips. This is a scanning electron image of that. This is quite old, actually. This is like more than 10 years old. The transistors of today are even smaller than that. So you can see the size scale here. This is about 100 nanometers. So that is really what has happened over the years, in the last, I would say, 40, 50 years, that people have made these transistors smaller and smaller. They have made them faster so that they can carry out these operations in a lot less time. And that is why the computers have become more and more powerful. Okay. So now, using this sort of a background, and the reason I wanted to go through this in some amount of detail, so that is I can compare how the quantum version of this calculation actually changes when you build quantum computing. All right. So now, moving into the quantum world, first we want to see what is it we are doing differently, or in fact, why should we even do something differently in the first place? So I think in the introductory lectures, you have been given some idea of quantum mechanics as well. And normally when we think of quantum, we are thinking of the subatomic world, the world of atoms and electrons. And one of the first early concepts one learns about, in fact, even in high school, you talk about how electrons are like in these orbitals around a nucleus in an atom. So, this is a very simple representation of, say, a hydrogen atom with one proton in the nucleus and one electron going around nicely in this sort of circular orbit. And it turns out that this model, which looks more like the solar system model of the planets going around the sun, is not really how things work in the quantum world. And a slightly more accurate picture is really that these electrons are sort of in these kind of hazy clouds around the nucleus, which means that there are certain distances away from the nucleus where they are likely to be found. But this very notion that the electron is at a particular location in its orbit is no longer a sensible question to ask. And I think Hariom would have covered some of these, and I saw that later on he would actually look into more of these slightly philosophical questions also about what does it mean to ask these kind of questions. But in the context of how the quantum description works, these different orbitals, or equivalently these different sort of fuzzy clouds, they are a very precisely defined state of an atom, of an electron in an atom. Which means that, and this is again sort of known even in the simpler model, that these, as you go to larger and larger orbits, they have more energy. So that energy is a way of labeling the state of the electron around the atom. So for example, you can now then say that if the electron is in this lowest orbital, which is now this fuzzy region closest to the nucleus, I'm going to label that as my 0. Just like you had those microscopic defects on a CD representing the bit 0. But now I've used this special symbol. This symbol is called a bracket. We will not go into the details of that, but this is just a way of labeling a quantum state. Okay. So this is not just a classical state 0, but it's a quantum state which is given by this, this vertical line and this little arrow, which together is called a bracket. And this can now state, so which means that the electron could be anywhere, but this entire configuration of electron being in that lowest energy orbital is labeled as the possibility of the system being in quantum state 0. Similarly, if you go to the next higher energy state, you can call that to be 1. So now we are starting to make some connections with the classical way of storing the information as bits. And so far, actually, I have not said anything which is very different. We again have two different states, 0 and 1. I've just told you in a little more detail what these physical states correspond to. I'll repeat it again. So if you are now talking about the hydrogen atom specifically, if the electron is in its lowest energy orbital, then we call that to be state 0. And if the electron is in the first, next highest energy orbital, we call that the state 1. Okay, but those are the only two possibilities. There are higher levels, so you could go to a system which is not binary, but we will restrict ourselves to binary right now. Okay, these states of these electrons in these atoms are really solutions to a wave function, a wave equation. So they are actually represented by waves. And because they are represented by waves and it is actually a linear equation, which means that combinations of those waves are also, which we call superpositions, are also possible solutions. Now, this is a possibility which was not present in our classical representation of the bits. Okay, so if we use these quantum states to store information, there is now a possibility to prepare this system in a configuration like this. It is a superposition of two waves, one representing the state 0 and one representing the state 1. And now, what do we call this? And this is where the whole problem of the mysterious nature of quantum mechanics and everything comes in. Unfortunately, in English or any other language, we say that, okay, this is now in both 0 and 1 at the same time. Right? That's sort of the naive way of saying it. Mathematically, there's a very precise wave function you can write down of what it means. But in plain language, we say that, oh, so now this quantum bit, if I did something like that, it actually is in both 0 and 1 at the same time. Now, this in the classical picture is completely nonsensical, because you actually don't want these strangely defined uncertain values, because those values have very precise meanings. And if it is something like this, then it has really it's neither here or there. And not just that, these superpositions can have signs. So I have written this as 0 plus 1, but you can also have a superposition which is 0 minus 1. And that also we'll say, okay, it is both 0 and 1. So this is this aspect that a quantum bit, which is created by storing information in a system where quantum states are supported. In this case, electronic states, states of an electron around a nucleus. This, by the way, is just an example. We will see later how we can do this in a more practical way. When you do that, you now have this new possibility of creating quantum states with quantum superposition. This is one of the most important differences and probably the central aspect of what all becomes possible when you introduce this new feature, which is coming from quantum mechanics into information storage. Okay. Now, such a system is called a quantum two-level system or a quantum bit, because a bit is again a two-level system, but now this is a quantum two-level system. It's a quantum bit, or in short, qubit. And usually you would express them by just showing sort of two lines here, one for the lower energy state, which is labeled this state 0, and the higher energy state, which is labeled state 1. Okay. Now I'm going to just introduce a concept which allows you to visualize these quantum superposition states in some physical form. Okay. So as I said that you can have these combinations of zeros and ones, it turns out that the most general combination of 0 and 1 is of this type. Now, in general, you can put any complex number, in front of 0 and 1. So these are basically the coefficients of your superposition, just like you can write a superposition of waves in terms of some numbers. These are the same numbers. And for a two-level system, it turns out that you only need two different variables to represent them. So one is this angle theta, and one is this angle phi. Okay. So you can see that as theta changes, the cos theta and sin theta will sort of change in different ways, and that will give you different weightages here, and you can also change the phi here. So a very convenient way of representing this somewhat complicated looking equation, don't worry about that too much. What you need to understand is that this entire system can be mapped to a point on a sphere. Or if you want to think about it in terms of a location on the Earth, it's really like the GPS coordinate of somebody's location on Earth. You have two numbers, latitude and longitude. So it's exactly the same. So you can think of this theta as the latitude, and you can think of this phi as the longitude. And for each point on the surface of the sphere, there is a unique mapping to theta and phi. And you can now see that if theta was, if theta by 2 was 90 degrees, then the cosine part is going to be 0, and the sine part is going to be 1. So that would correspond to the state 1, which is pointing on the north side. And in the other way around, if theta is 0, then this goes to 0 and this becomes 1, and that's one thing. And then there is a whole range of other possibilities in between. So for example, all these points which are right in the middle, for the Earth, it would be like points on the surface of the equator. These are points which will have equal values for sine theta and cos theta by 2, right? And that's basically 1 over root 2. But then again, there are many, many different possibilities of phi, which would correspond to the arrow pointing in different directions along the equator. So again, in the equator, you can go all the way around in a circumference. And then that's where you get these different possibilities. Okay. Now, the moment one represents a quantum bit like this, one very important question comes, is it really a two-level system? Right? And this is actually something which is often leads to some basic confusion about quantum computing. Now, earlier I explained to you that classical bit can take two different values, 0 and 1, and if you want to store larger numbers, you have to add more bits. I have only talked about one qubit so far, right? And now I'm saying that, okay, it can be here, it can be there, it can be anywhere on the equator. In fact, it can be anywhere on the surface of the sphere. So if you think about it, how many different points are possible on the surface of the sphere? It's infinite. right? I mean, I can have packed points as close as possible, and we have very small variations between theta and phi. And that just means that there are an infinite number of combinations to be able to put on the surface of the sphere. And in fact, you can prepare the system in all of those different possibilities. And the way you actually prepare them is, in the most general case, there are details depending on the physical system. You actually send in radiation at an energy difference corresponding to these two different levels. And by controlling how long this pulse of radiation is, how tall or how strong this pulse of radiation is, you can put the system anywhere on the surface of the sphere. So are we really talking about the fact that one qubit can now store infinite possibilities? That just seems like there's infinite amount of memory available. I can store all possible combinations. And this is where the second aspect, strange aspect of quantum systems comes in. The answer, of course, is no. You cannot use a qubit as a source of infinite capacity to store. And the reason is that, remember that just storing information is not enough. When you copy a file after doing some work in school and you bring it back in your flash drive to your home and you put it onto your computer, it better recover the same file which you stored in your school, which means retrieval of information or measurement of the state of that of the bits, of the many and thousands and millions of bits which are there in your flash drive, is also equally important. And this is where the quantum system behaves in a very strange way. And the simple answer is that if your quantum bit was in the state 0, if you measure it, it will give you that the answer is 0. It will say, I am in state 0. If your quantum system was in state 1 and you measure it, it will give you the answer that I am in state 1. So far, it looks exactly like what you would expect a classical bit to behave like. But now when you talk about a state like this, which is a superposition state, or any other point on the sphere, which is not at the two different poles, when you measure, it actually does not reveal that particular point. It again either gives you 0 or 1. And this is, I want this to sink in. I'm not sure if Hariom has covered the measurement aspect, but this is often, you might have heard this phrase, collapse of the wave function. Initially, it was in this state, but when you measure it, you get an answer which is 0 or 1. Even worse, that answer is completely random. If you prepared a state like this, which is exactly in the middle, there is a 50% chance that when you measure and ask this qubit what state you are in, it will give you 50% of the time an answer 0 and 50% of the time an answer 1. And there is no way to predict which answer you will get. It's completely random, just like you hope the toss of a coin is. Okay? So which means that when it returns, when the qubit returns the information it has stored, it is still only one bit of information. The answer is still 0 or 1. But on top of that, you have this added complication that it is completely random. So you realize now, if you think about it, I cannot really use all these infinite amount of points to store and retrieve information as the most basic operation you would do for any memory. So it's true that you can encode, you can put lots of different possible states, but when you try to recover this information, you only get one, you only get answer which is one bit, which is 0 or 1. Okay, this is something very strange about quantum mechanics. No one really understands. There's no way to predict what random answer you would get. And just as I said, if you are close exactly at the equator, it will be a 50-50% chance. But if the state was closer to, say, the 1 state, then there will be a higher chance of getting 1 and a lower chance of getting 0. And similarly, if the state was closer to 0, you'll get a higher chance of getting 0 and a lower chance of getting 1. And this probability, this randomness, is given exactly actually by the square of this number. So cos squared theta gives you that value. What is the probability? It's random. It gives you the probability of getting the answer 0. And sine square theta gives you the probability of getting answer 1. Now, if you remember your trigonometric identities, sine square theta plus cos square theta is always equal to 1, which is what you would expect, because the probability should add to unit probability, because one of the two options have to happen. Okay. So this is the strange thing. So a quantum bit does not offer you an infinite memory possibility. It just offers you a possibility of being in infinite possible configurations, but at the end of the result is still you get 0 or 1. Okay, and this is what happens when you measure a quantum system. Remember that a classical computer doesn't contain one bit. It has millions and millions of bits you want to store and manipulate. And similarly, a quantum computer also needs more than one qubit. So for example, if you now have two different qubits, and here I've shown them, with two different energy levels separation. So this one has a smaller gap, this one has a larger gap. So this is one qubit and this is another qubit. Just like in classical bits, you can represent a 2-bit number using 2 binary digits. So another way of representing the states, the different possibilities which are there for a 2-qubit system, you can label them by combining these two numbers. So you can say 0, 0, 1, 0, 0, 1, and 1, 1. So just like the classical bit, 2 different bits have 4 different possibilities, but the difference is that these 4 different possibilities now, if you see, I've again put these special symbols, these are all different wave functions. So in some sense, these are like different types of electronic orbitals, more complicated orbitals, which are possible now. But there are now 4 different states as opposed to 2 different states for the single qubit. And the most general state, the general superposition state, is now a combination of all of these 4 numbers. Okay, going back to this, remember that here I had something multiplied by 0 and something else multiplied by 1. Now for the most general 2-qubit case, you will have 0, 0 multiplied by something, 0, 1 multiplied by something, 1, 0 multiplied by something else, and 1, 1 multiplied by something. So there are now 4 different numbers over there, and it no longer is possible to visualize this in a simple sphere. So that simple picture only works for 1 qubits, and after that there is no simple picture to represent this. Okay, and I want to point out one other interesting aspect of quantum mechanics, and that shows up even at the level of 2 qubits, is there are different types of 2-qubit states. Remember that I can choose any combination of these 4 different possibilities. So if you had a combination like 0, 0, and I ask you to describe what state this is, you will say, well, first qubit is in 0, second qubit is also in 0, right? That's a very straightforward thing to do. Similarly, if I gave you the state 1, 1, you'll say, yeah, first qubit is in 1, second qubit is also in 1. Okay. What about a state like this? You see, this is now a valid superposition state. It's the superposition of this state and this state. And here, if you think about it carefully, you say, okay, the first qubit is 0, and it's also here is 0. So yes, okay, this looks like the first qubit is in 0, but the second qubit is in a superposition of 0 plus 1. So which means that here, for this kind of a superposition state, I can still describe the 2 qubits separately. The first qubit is here, and the second qubit is in a superposition of these 2 states. But what if you had a state like this? 0, 0 plus 1, 1, which is a perfectly allowed solution for a 2-qubit system. It turns out that there is no simple way to describe this in terms of the properties of individual qubits. Now you might say, no, that doesn't sound right. This just means the first qubit is in a superposition state and the second qubit is also in a superposition state of 0 and 1. Turns out that's not really correct, because if that was the case, you would actually have 4 terms. You will have 0, 0 plus 0, 1 plus 1, 0 and 1, 1. That is what represents a state described by the first qubit being in a superposition and the second qubit also being in a superposition. Now, this type of a state has no description in terms of individual qubits. In fact, these are what are called entangled states. The funny thing here, though, is that if you measure one of the qubits, then the fate of the other qubit is sealed. Because remember that these are again in some combination, so which means if you try to measure the first qubit, you will get again an answer which could be either 0 or 1 in a random sense. And if you measure the second qubit, again you would get an answer which is random 0 or 1. But if you measured the first qubit and immediately asked what is the state of the second qubit, then you have this very interesting property that if the first qubit was measured to be in 0, the second qubit also has to be in 0. It no longer remains in any superposition state. Similarly, if the first qubit was measured to be 1, the second qubit is measured to be 1. And again, I'm bringing this up because this property of entanglement is quite crucial to quantum computing. And you will see in an example coming up later where we discuss this, why this is important. Okay, and this is also what often is referred to as the Einstein's, there's the EPR paradox. Some of you might have heard about it. Einstein was extremely unhappy that this was possible because it seemed to indicate that even if these two physical qubits were far away from each other, somehow doing something on the first qubit instantaneously decided what happened to the second. But this is important. It's not so easy to create these kind of states, and it's a very important thing for quantum computing. Okay. So now, keeping these things in mind, what does a quantum computer at the end of the day do? What is going on in it? And this sort of block diagram represents the basic operations. So you need many, many qubits, and each of those qubits can, start with some representation in terms of a superposition state. And then there is this magic box U. So this U is, in the mathematical jargon is called a unitary operation, but let's not worry about that. It's basically a sequence of operations which transform each of the qubits into some other state. It also creates those entangled states I talked about. And it's essentially all the steps that need to happen for the computation to proceed. So in each of these operations, the state of this n qubit system, and remember now, if you go back to this idea that one qubit had 2 states, 2 qubit had 4 states. Similarly, if you have n qubits, 2 to the n states are possible. And you have to describe the full 2 to the n system to be able to understand what's going on. And once this is done, you have to go and measure all the qubits. And remember again that all the measurements will either yield a 0 or a 1 because you're measuring each individual qubit. And somehow the strings of zeros and ones you get has to be your right answer. That is the answer you get. Remember that a quantum computer at the end of the day has to reveal some classical number as the answer. Otherwise, we don't know how to interpret that result. So this is again important to keep in mind. So all the magic happens here. All those infinity of states which are being explored happens in this part of the thing. But at the end of the day, when you measure, you still only get n zeros, n bits of information which are all zeros and ones. Okay, so it's this idea that if you have n qubits as opposed to n classical bits, you can have all of these 2 to the n different states present at the same time. And this is the power of the exponential. By the time n is a modest number like 300, we're talking about 300 qubits. I want again you to pause and think about this. A typical mobile phone has 4 GB RAM, which means 4 billion bits in it. And I'm talking about only 300. It's an insignificantly smaller number than the typical amount of bits we deal with in classical computing. But 2 to the power 300 is such a large number. In fact, it is roughly equal to the number of atoms in the visible universe. And it's the fact that you are able to play around with all of these extremely large number of states is what gives the quantum computer the power to do some amazing things. But remember, it is not a memory with that many different possibilities, because at the end of the day, you only get n bits. It's the ability to play around with this very large space. And when you do these operations, you are actually changing the states of all the 2 to the n states in the system at the same time. And you can do that very easily, even though you're doing operations, in only about 300 qubits, you're manipulating a system whose effective size is equal to the number of atoms in the entire visible universe. So it's just mind-boggling, and that's where this power comes from. But if you really want to exploit it, you have to use this property of interference and parallelism. So parallelism is something I already mentioned. There are this enormous number of states, but all of those states, remember, these are waves. They can cancel each other. They can reinforce each other. And the algorithm, which is going on here, which is basically the computer program, the steps, has to evolve its system in a very careful way that all the wrong answers sort of interfere and cancel out, and only the correct configuration of zeros and ones emerges. Okay. Now, later on, I will give you some examples where you get a feel of how this actually happens. Okay. So this is really the essence of what a quantum algorithm. Can we not do this on a classical computer? And why is this a perfectly valid question? Is because I know how to write down these equations. I know exactly how to write down this on a computer. And I can then do these calculations. Turns out that these calculations are nothing but multiplying big matrices. And that's actually the key operative word, big matrices. I will need to store 2 to the n numbers, roughly, to be able to even handle an n qubit system. Now, if it's n is 2 or 3, it's very trivial. Even up to 10 or 20, it's no problem. So remember that even at n equals 300, there is no computer in the world which can have that much memory or processing power to handle that. In fact, it turns out that it's around 50 qubits, which is the rough number where the most powerful computer sort of gives up. It cannot store, it's just too much memory to handle all these numbers. But on a quantum computer, you only need 300 qubits. So I hope you sort of see this crazy difference which is going on. You need 300 physical objects to represent a 300 qubit system in a quantum computer. But in a classical computer, you need something which has a memory of the size of 2 to the n. And 2 to the n is enormously large. And you just cannot do it on a classical computer after that. I want to now quickly go through some examples which sort of tell you why this superposition and entanglement allows you to do things like somewhat differently than what is possible in a classical computer, and how that gives you some sense of why a quantum algorithm might be more powerful. Okay? So first, this idea of quantum superposition. So remember, to remind you again, for a single qubit, there are 2 possible states, and you can create a system in a superposition of both those states at the same time. For 2 qubits, there are 4 possible states, and you can create a superposition of all the 4 at the same time, right? So that's really the thing, that all of these, these states can be present at the same time, and that's where the power comes in. So we will see a particular example, and this is actually an algorithm invented by an Indian scientist called Love Grover. He did it when he was in Bell Labs in the US many years ago. This is sometime in the 90s. And it's a very simple problem, okay? So here you have a table of input and output. Again, I've written them in binary. It's a 4-bit number, which goes from 0001 all the way down to 1111. I guess there should have been an element 0000 here as well. And the output for all the inputs is always 0, except for one special combination, which in this case is shown as 0101, where the output is 1. Okay. So imagine that there is some kind of a computer, a regular computer, say a classical computer, a black box, where you are asked to find out which special number will you get the output 1. Okay. And the only option you have is to feed in these inputs and see what the output is. So the problem really is that what is the fastest way you can find which is that special item? Remember, this special item in this example is 0101, but it could be any of these numbers. You don't know a priori. Okay, you have to find out, your job is to find out which is the special item here. And the only way to do this is that you send in some number. You will send in, let's say 1100, the computer will output 0. If you send in 0101, and then you get lucky and you get the answer 1 in the second step. But if you think about it, on an average, how many such operations you have to do before you get the right answer? If you got lucky, and the chances of that luck is basically what? 1 in 16. There are 16 possibilities. So there's a 1/16th chance that in a single shot, you will get the correct answer. But if you're unlucky, you could also get it in the 16th slot, because you don't know which one it is, and you would be randomly choosing them, and you could choose the correct one as the last option. So if you analyze this, using computer science techniques, you will see that roughly you will have to at least guess half the number of entries. So if there are 16 entries here, you have to roughly guess half the number of tries before you get lucky and you find the correct answer on an average. Sometimes you'll get it in the first, sometimes you'll get it in the last step, but on an average, you will get it at roughly the 50% of the total number of steps. This is the only algorithm that is possible in classical computing, and that's the best you can do, right? So this is sort of like a search problem where there's one special thing and you need to find which one it is. But what Love-Grover figured out, that if you had a quantum computer, you can actually do something differently. And what is this difference? It's this possibility of sending all these inputs at the same time. Because remember that the input is represented by a 4-bit number. And in the classical case, you can only choose one of the 16 possibilities at any particular time. But in a quantum computer, you can create a superposition of all the 16 possibilities at the same time. So now you start to see how a quantum processor is somewhat different than a classical processor. Okay? So this is sort of now a diagrammatic representation of a 16-qubit system. And again, it's labeled from 0, 0, 0 and 1, 1, 1. And remember, the most general quantum state is basically some number multiplied by 0, 0, 0 state, some other number multiplied by the 0, 0, 0, 1 state, and so on and so forth for all the 16 combinations. So it's a superposition of 16 quantum states labeled from 0, 0, 0, 0 to 1, 1, 1, 1. And the height of this pillar is basically a representation, sort of a diagrammatic representation of the value of that coefficient. And remember earlier, for a 2-qubit system, I had told you that this coefficient actually gives you the probability of getting that answer when you measure it, right? So it serves both the purposes. So in this case, I have created an equal superposition of all the 16 possibilities, which means that if I measure it, I will randomly get one of the 16 answers which are possible. Okay, so that's the starting point. So at this point, it's completely useless. Just as there was a question was asked, it's going to be a completely random answer. You're not going to get anything useful out of it. But now, as the algorithm proceeds, there are 2 steps in this algorithm. And these steps basically do is that now, just like the classical computer, when you fed in the number, it gave you the output. A quantum computer, what it does is that if you feed in these numbers, which is 0, 0, 0 or 1, 1, 1 or a superposition state, what it does is that it retains the sign of this coefficient for all the numbers except for the special one. So remember that the special number was 0, 1, 0, 1. So if you had sent it, it basically flips the sign. So remember, in superpositions, you can have signs as well. So it basically makes it negative. So if you send in an equal superposition number like this, what comes out is something which is like this, where the sign of this, so it's like some number times 0, 0, 0 plus some number times that, but here it will put a minus sign, just like we had talked about 0 plus 1 and 0 minus 1. Okay. And in the next step, what it does, it now takes the average of all these numbers. And remember that because one of these numbers has been made negative, the average is represented by this dashed line, which is slightly below the maximum value. If all of them are pointing at the same point, then the average will be exactly at the top of these bars. But because one of them is negative, the average will be slightly below it. And in the next step of the algorithm, they basically flip everything around this particular mean value. Okay, what does that mean? It looks something like this. So the mean is here. And if you flip something around it, it means that this thing goes all the way to the top. And these things are flipped equally further away. So basically what it means that the distance of the top is the same, but now in the opposite direction. So all of these ones which were positive before, they have gone slightly below this dashed line. And the one which was negative has now gone really far up over there because it was so far away. When you flip it, it goes to the opposite side. Now, if you see what has happened is that the probability of that special state has gone up compared to the relative ones. And that's the essence of the algorithm. It amplifies the probability of the correct answer. And you can do the same step again. You now take this as the input, put it back into the quantum computer, and then it again gives you this inverted output. You do the mean, you flip it again, and now this time all the other things go even lower and the special item becomes even larger. And what Lovegrover calculated is that if you have a problem with n inputs, so in this case n is 16, remember that in the classical case I told you that you have to roughly do it for half the number of steps, which would be about 8. What he found out that in the quantum case, you have to only do it for roughly square root of n steps, which in this case would be only 4. So in 4 steps, this special item would become almost close to unit probability, whereas all the other items will become very close to 0 probability. And now at this stage, you can measure, and then you will get the answer 0101 with very, very high probability. So this is actually a very nice example which tells you how by starting with a superposition state, you can operate on all of them, and how as the algorithm progresses, the correct answer's probability increases while the wrong answer's probability decreases. So it really contains both these nice aspects in that. And the advantage is that instead of n by 2 steps, you can get the answer in about square root of n steps. Okay. Now, for something like 16, it doesn't seem like such a great improvement because classically it was 8 steps and quantum mechanically it was 4 steps. It's still twice as less number of steps. But as n becomes bigger and bigger, this difference between n and square root of n will grow larger and larger. And that is where it really starts to benefit. Okay? But this is a much simpler example to understand than some of the other complicated ones, which I will also briefly mention. Okay. So this really tells you that the superposition, the ability to process all of the states at the same time, is one of the key features of quantum algorithms. Okay. And this other example, one of the most famous examples, in fact, is the Shor's algorithm. And this is related to finding prime factors of large numbers. Okay. So this example shown here is that you have 2 numbers, and both of these numbers are actually prime numbers. If you ask you to multiply them, this is a very easy problem. Anyone can do it. Even small kids can do it. Using a calculator or a computer, this is trivial. But if I give you this product, and I ask you to find out which are the 2 numbers which are multiplied to get this answer, that turns out to be not such an easy problem. So this reverse problem is very hard. For a number of this size, it's still not very hard. This can be done on a regular computer in a couple of seconds, maybe even less. But as this number becomes bigger and bigger, the problem becomes exponentially hard. And this aspect, that finding this reverse problem is very difficult as the number becomes bigger, is very important, and it's used to secure your data. Every time you do an ATM transaction or you go to a secure website where you're typing passwords, this idea is used. And basically the idea here is that you encode the information using this number, and you can decode it only if you know the individual numbers here. And if somebody intercepts your message, they will need to know these individual numbers. But if they only have access to this, they will have to solve this reverse problem, and that is currently impossible, provided this number is very large. In fact, this called the RSA encryption technique. And what Peter Shor found out, again working in Bell Labs, he's now at MIT, he was at Bell Labs at that time in 1994, that he figured out that this problem on a quantum computer doesn't grow that much harder as the size of the number increases. So in fact, you get some completely crazy answer, is that if you have a 1,000-digit number, a regular computer would take something like 10 to the 24 years. I mean, this is an unimaginably large number, whereas a quantum computer will only take 20 seconds. So it's basically an impossible problem becomes possible in very quick time. And in fact, it was this invention of this algorithm, and along with the Grover's algorithm, which really made people very excited that, okay, if you are able to build a machine like this, you can really do some amazing things. And And this was really the beginning when people started building the hardware for implementing such ideas. Okay, this is something I mentioned in response to one of the questions, is that because the behavior of the nature around us, which is physics, chemistry, and biology, ultimately is rooted in the laws of quantum mechanics, and solving quantum mechanical equations on a regular computer is extremely hard. But what he said is that because all quantum systems are in some sense equivalent, you can make your quantum computer, which is a different quantum system, mimic the behavior of some other quantum system which you're trying to understand, maybe some chemical reaction, or you're trying to design some new material. You can actually make it behave like that in a lot more efficient fashion than a regular computer can do. And in fact, a lot of the scientists are very excited about this possibility, because this will actually completely change how research is done in the future. You now can do a lot of these calculations on a quantum computer. We are not there yet. We have not built such machines, but it is one of the most exciting applications, is really understanding nature better. And this would really give us much deeper insights and lead to many, many more discoveries. So in fact, a quantum computer, or in this specific context, it is often called a quantum simulator, is really an enabler of making even more exciting discoveries in science and technology. Okay. One of the early applications, as I've already mentioned, that because chemistry's underlying principles are coming from quantum mechanics, you can actually solve them a lot more efficiently. But today's quantum computers are not really that powerful yet, and I will mention why in a little bit. But people have done some simple experiments. So for example, they have solved very simple molecules like hydrogen, lithium hydride, and beryllium hydride. Okay. And I want you to just pay attention on, and this was done on a 7-qubit quantum computer about 3 years ago. The result they are actually calculating is so simple that it can actually be calculated by hand. There's a formula for that. But this was really to prove that these kind of calculations can indeed be done. It's like mentally calculating 2 plus 3. It's possible to do, but you can check that your calculator is actually working by checking. So this is really that. It's a very simple calculation. You don't need a quantum computer to do it, but you check to see if the ideas are working. Okay. So this dashed line here is actually the correct answer. And these black dots are the answers obtained by the quantum computer. So for the hydrogen atom, it looks fairly accurate. The dashed line and the experimental results are matching. But for lithium hydride and beryllium dihydride, the black dots are actually very far away from these lines. But they sort of work, right? And this is because the current machines we have are full of errors, and they give wrong answers quite often. And that is the reason this is not working. But it sort of shows that the basic principles of this idea are solid. We just have to make the machines better. Okay. People have also done some problems in biology, for example, photosynthesis. And by the way, this is again done using a particular technology which I will mention called superconducting qubits. And here also, this is also what was done using superconducting qubits. And they were able to make a model for photosynthesis and show that they can mimic a particular operation in photosynthesis where the role of the environmental noise was emphasized. Okay. So, these are not very important to understand. I just wanted to give you a flavor that there are all these different things which are possible using once a quantum computer is built, and people are already trying them with small quantum computers. In fact, this particular quantum computer only had 3 qubits in the experiment. Okay. And there are a host of other possibilities which people are exploring. You can do chemical reactions, which basically means, at least I was a physics student and I never liked chemistry, mostly because the labs used to smell a lot. There could be an imaginary future, or not an imaginary future, but a future where a lot of the initial chemical reactions might not even have to be done on a real lab. You could just do it on a computer, and once if you're developing a chemical reaction, say to make some medicine or some kind of a special chemical, all the production can be done at the final end in a factory, but all the testing and the early experiments could be done on a computer. So similarly, you can make new kinds of medicines using this technique. You don't have to carry out actual experimentation. You can just test all of this on a computer. Similarly, for new materials, new kinds of, you can arrange the atoms and the molecules in different ways and test if that works just by solving those equations on a quantum computer. There are also non-science sort of related problems like optimization problem. There is this very famous problem called the traveling salesman problem, right? Where a person has to deliver some 10 packets and he or she needs to find the most optimal route to take in order to cover all the destinations, but want to spend the minimum amount of distance on the road and save fuel. It turns out that's a very hard problem, but it's a very relevant problem for delivery companies. And turns out that the quantum computers can be very good at something like that. And it's for the same reason, is that there are many, many different combinations which are possible in this traveling salesman problem. And an appropriately designed quantum algorithm can look at many of those possibilities simultaneously because of this superposition possibility, as opposed to a conventional computer which has to look at it one at a time. You look at it and they say, okay, this is better than that one is not so great, and you have to go through it in serial fashion. Okay, so then these are all related to image detections, logistics, routing. Even something very complicated like weather prediction could have improvements what one uses quantum computers. And the really exciting possibility is that we have probably not even scratched the surface here. This is partly connected to the fact that writing quantum algorithms is very complicated and requires some very deep understanding of how to exploit these superpositions and interferences. But there are many, many more things yet to be discovered. We don't even know what all other things could be possible. Okay, we were now at the stage of how to actually build. What is this quantum computer look like? And I will, I'll give you a brief introduction. So remember, when I started the quantum discussion, it was with discussion of atoms and electrons and atoms. And it's sort of natural to think about atomic systems when you are thinking about quantum mechanics. And in fact, one of the most popular and I would say most advanced technologies is actually by using individual atoms, or more precisely ions, because some of their electrons are removed. But this is not the hydrogen atom. These are more complicated higher atoms like calcium, ytterbium, and so forth. So this image, what you're seeing, is actually two such atoms which are trapped in midair, in vacuum, by applying appropriate electromagnetic fields, and they are actually giving off light. So you shine laser on them and they sort of re-emit that light, and that is what is being detected here. And typically the space between these two is about a micron or a few microns or so. So this is about 1/1,000,000th of a meter, even smaller than, much smaller than the width of a human hair. And you can then use the electron energy levels in that particular atom. So this is no longer the lowest energy level, because remember, calcium has many filled shells. So it's some other appropriate level which they choose, and you can then manipulate that by applying lasers and other kinds of electromagnetic radiation to change the quantum states, just like I told you earlier. And this is one very promising technology. In fact, one of the first experiments on doing, being able to isolate a single qubit was done using these trapped ions. And in 2012, the person who did that was one of the recipients of the Nobel Prize. Similarly, you can actually even just trap a single electron. So here you're talking about electrons which are part of an atom. Here you're talking about actually confining an effective electron on a chip. These are called quantum dots, and both of these have been fairly successful. I would say trapped ions are a lot more successful and advanced than this particular technology. And here is an image. This is again sort of a blown up image of showing you a whole string of such ions. I think there's probably some 70 or so in this string. There was a company which was recently launched maybe about a year or two back called IonQ, and they have made this special kind of a system which can trap these about 70 ions at the same place, and each of these dots represents one qubit. And they have shown that out of these 70, they can actually play around with about 11 of them very efficiently. It's not possible to control all of them very well right now, but it's quite an exciting and one of the more accurate quantum computers. This seems to make less errors than the other promising approach. And using this electron idea, also people have made chips. The people have made like systems which can accommodate up to 9 such electrons, and each of the electron now represents a qubit. And here I'm not going to go into the details, but basically a single electron can behave like a magnet. So the qubit is whether the magnet is pointing in this direction or this direction. So by pointing, you mean like, the direction set by south pole to north pole of that particular magnet. Okay? But the technology which is currently most popular and most heard of in the news, and it's also the area where I work in, is called superconducting circuits. Okay, and basically the superconducting circuit qubit is an oscillator. I've shown here a picture of a pendulum, and just like when you set a pendulum moving, it oscillates back and forth at a particular frequency. This kind of a circuit, and this is an image here, you can see the size scale. What you're looking at is, this light blue colored and here this gray colored is basically the material aluminum. It's very thin aluminum, about 100 nanometers thick, which is deposited on a chip, say a silicon chip or not. And this is the size of one of these qubits. It's actually quite big compared to an atom. Remember, the size of an atom is about, on the angstrom scale. Whereas here, this is almost 1 millimeter. You can actually just see it if you look very carefully with your naked eye. But yet, at appropriate, when you use this under appropriate conditions, it can be used as a quantum bit. Okay, and this is the circuit diagram. And what is the qubit here? Just like in the atom states, it's the different energies of the electron. Here, it's the different energy of oscillation. So remember that for an oscillator like a pendulum, if you have a larger amplitude, it has more energy. If you have a smaller amplitude, it has less energy. So there are two different states which have small energy and large energy, and that is what you use. And again, just like an atom, an electron in an atom, you can now create superpositions of those different combinations. So, in some sense, it's like a little bell, which if it is ringing very softly, it is quantum state 0. If it is ringing a little bit more loudly, it is quantum state 1. And the difference in energy between these two is extremely tiny. It's like very, very small amount of energy. And in order for these to work, you have to cool these devices down to very, very low temperatures, close to absolute zero. Actually, you work at a temperature about minus 273 degrees centigrade. And only under those conditions, this quantum behavior actually manifests itself, and you can actually do that. And the correct frequency of electromagnetic radiation, remember I told you have to shine electromagnetic radiation to change the states. That now is in the microwave frequency regime, similar to the ones which are used by your cell phones to communicate from one place to the other, or in your microwave oven, a little higher than that frequency, but in the microwave regime. Whereas in the trapped ions and all, you use lasers, which are in the optical frequencies, much, much higher frequency. These are a lot lower in frequency electromagnetic radiation. But this is one of the most popular and most advanced technology for building these quantum bits. And typically, these kind of chips are put inside boxes like this for if you're doing very simple experiments. This is the same chip I showed you yesterday. And this is just really a piece of copper, about a few inches in dimensions. And these kind of boxes are useful for doing simple experiments with maybe only one qubit. But if you want to do a lot more, I'll show you some examples of the kind of chips which exist. And all of this requires, fairly sophisticated control and measurement electronics. The picture on the left here is that of that special machine which allows you to cool down to those very low temperatures. This is a commercial machine. You just have to buy it. And then you stick your devices at this lowest plate here, which is the one which gets the coldest. So the different temperatures are indicated here. And this is the one which goes to the lowest temperatures. You have to do all kinds of filtering and special wiring to be able to control these things so that you can send those microwave signals to control the devices. You need specialized amplifiers to be able to detect the signals from this. Remember, you have to measure them in order to find the answer. And these systems are so delicate that you have to use extremely small amount of these microwave radiation. So detecting them is also a big challenge. And if you remember when Vinay was introducing me, this was one of the areas I focused in during my PhD and postdoc on how to build these very sensitive detectors which can detect even the tiniest and the smallest amount of signals present coming from these experiments. And that has now become sort of the standard method for measuring all of the superconducting qubits. Okay, and then just to give you a sense, because I remember I mentioned that you have to have more than one qubit and you need to do these gates, just like you have the AND gate and the NAND gate. In order to connect two such qubits, it's actually like you have two pendulums and you just sort of connect them from the same. So in the circuit language, it's actually just connection by capacitor. So maybe some of you have seen some videos or even done this experiment where you have two pendulums hanging from the same wire, and you keep one pendulum stationary and you move the other pendulum, and then slowly this pendulum starts to move, and then this one slows down, and then they sort of do this dance back and forth. That is actually the physics, very similar physics, which happens to be able to implement 2-qubit, multi-qubit gates here, so that you can do more complicated operations of creating the entangled state, which I had mentioned earlier. Okay. Now, when you put many of these qubits together, you get, chips which look like this. So this is now quite an old chip from maybe 6 to 8 years ago. Each of these little crosses you're seeing is 1 qubit. And there are these control lines coming from both directions, which allow you to change the state of that qubit by applying microwave radiation. And they're all sort of in this one line with each other. This is a 9-qubit chip from University of California, Santa Barbara. Then many of you might have heard that IBM is very heavily into this research. So this is an example of a chip from the IBM group. There are 4 qubits here, these boxes here, and again, lots of these squiggly lines for measurement and control. This is another chip from IBM, which has many more qubits. This one has 16 qubits in it, and many more squiggly lines for control and measurement. And all of this have to go inside a similar dilution refrigerator I showed you. But now when you have many, many qubits, you have lots and lots of wires. So this is actually a picture from one of these qubits stored. I'm really showing you this to explain the level of complexity of building a system like this. There's lots of wires, there's lots of boxes, and you have to protect everything from all kinds of noise in order for this to work. So that's why this is not really a completely solved problem. We're still working on figuring out how to do this very, very efficiently. And then most recently, some of you might have seen in the news last year, Google came up with this new chip design called the Sycamore, and they demonstrated something called quantum supremacy. Okay. Now, this is a fairly controversial topic, but the essential idea is this. So remember, I told you that if you have a small number of qubits, you can actually test it on a classical computer on how it works. And it's only when the number of qubits becomes large enough that it becomes more and more difficult for a classical computer. So small qubit systems are not better than classical computers. Only when you have a sufficiently large number of qubits with sufficiently small, errors that they don't do bad things every once in a while, that it becomes powerful. So they wanted to show that they have reached that limit, that they have solved a particular mathematical problem, which even the most powerful classical computer in the world will not be able to do in any reasonable time. So I think they had estimated that something they had done in about few minutes would take 10,000 years for even the most powerful classical computer, which is like this big supercomputer they had access to. And that result was controversial. Another group said, the IBM people said, no, it doesn't take 10,000 years. But this is an ongoing sort of debate. But this was a very important milestone, and new experiments will show this. And remember, that is very important. Unless you can show that your quantum computer is doing better than anything else which is out there, there's no motivation to keep building this. So this was a very important milestone, and this will happen larger and larger, better and better as time goes on. Okay. So just to summarize, what does it go at the end? What all do you need to really build a quantum computer? And it can be sort of narrowed down to some very key ideas. You need some physical quantum two-level system. It could be an ion, it could be an electron on a chip, or it could be a superconducting circuit, and some two appropriate quantum states which are present in that. Okay. Then you need this, the state preparation, or prepare the quantum states. You need to be able to prepare any of these different possible states which are possible for that two-level system. You should be able to measure them, because at the end of the day, you have to find the answer. So after the computation is over, you need to be able to measure them very precisely. And then finally, you have to be able to create interactions between these qubits so that you can do these gates, the equivalent of the NAND gates and the AND gates for the quantum system. Without that, there is no quantum algorithm. So by combining all these operations, you basically evolve an algorithm. And it sounds very simple. It's like, okay, this is like very straightforward. Everything seems to have already been done. So what is the problem here? And the problem is that these quantum systems are extremely fragile. Okay. And what do I mean by that? And this is sort of going to probably shock you, but this is really a very important point, and an area which needs a lot more work, but already there's a lot of progress. So I had mentioned this earlier, that systems always try to come back to its ground state, the lowest energy state after some point of time. Now that's fine, but if that happens for a quantum bit, then really what I'm saying is that if I take my quantum system and I put it in the excited state, I've prepared the number 1, the quantum state 1, after some point of time, it's going to come back to the state 0. This is equivalent to losing the information you originally had set. Doesn't matter, you could have prepared a superposition state, after some point of time, it will come back to 0. This is almost like erasing all the information you had. And this usually happens on a particular time scale, which is given by T1. It's called T1, just a label used to represent that number. And this number for superconducting qubits is about 100 microseconds. In 100 microseconds, the states will be completely, or everything will just come back to 0. Most of them will come back to 0. It's a probabilistic process. That sounds terrible, and it is. And that's not the end of the story. Remember that this phase is also very important. So if you have something on an equator, which is the equal superposition of 0 and 1, it could be anywhere along that phase, and where it's pointing is very important for the computation to proceed. And there is another kind of noise called dephasing, which actually makes this equator, this arrow in the equator, point in different directions randomly over time. So over another characteristic time scale, you have no idea which way it's pointing, because the noise has completely made it point in some random direction. And this time scale is also of the order of 50 to 100 microseconds, maybe about 100 microseconds or larger for superconducting qubits, and it's slightly different for other platforms. So currently, there is no solution for this. People are working on making this time larger and larger so that we have more time. But what it means is that today's quantum computers, they have to finish their calculation in a time much, much shorter than this. And that is why they are giving wrong answers every once in a while. And this is a fundamental property of all quantum systems. They interact with their surroundings, and this bad stuff happens. This is what is called quantum decoherence. And it's one of the biggest challenges. And then you have to make it work for many, many, many different qubits. As you do that, it becomes a lot more difficult to control this. Nobody has shown that it's impossible that you will be able to do it, but this is one of the fears. But so far, things are looking good that we have been able to improve. In 1999, when the first superconducting qubit was invented, this number was about 5 nanoseconds. Today, that number is close to, the best results are close to a millisecond. So there's a lot of improvement which has happened, but we still need to improve it even further. And there are other specialized techniques which allow you to circumvent some of these problems in a more complicated way, but that also requires that these numbers are improved a lot. Okay, so that's basically what I wanted to say. I sort of want to leave some points here, as people who might in the future join this race to build a quantum computer. There's actually many different angles from which you can come on. You need physicists who are inventing these new kinds of designs and analyzing what noise sources are affecting them. You need experimental physicists and engineers to actually figure out how to put many of these qubits together. You need computer scientists to develop algorithms, both on current computers which are slightly have errors, and future computers which will hopefully have solved those errors. And we need chemists and biologists and other kinds of people who are going to figure out how we can exploit these unique properties for making the solution of various problems better using quantum computers. So there's really many, many different avenues, and that's really one of the most exciting aspects, is that a lot of people with various backgrounds and expertise are coming together to work. Okay, so let me end with that, and of course we have to get it all to work, and we're all sort of working on those challenges.
I am Mokshit Kothari, and I'm here to present the vote of thanks. Sir has explained a massive topic and all its multifaceted components in just 2 hours. He has articulated how the hardware works, how the basic software is, and its applications in some fields. I am sure that a lot of people here are inspired by today's session and will, of course, try to become engineers and scientists who actually advance the field. So, thank you for inspiring all of us. Thank you for sharing all this information. And I am sure that some of us will in future contribute to this field, and it will be all thanks to you. Thank you.
Thanks a lot, Mokshit, for your kind words. And yeah, thank you to Vinay and Hariom also to invite me to the platform. And thanks to the audience. And